Chapter 5 Forces and Newton's Laws of Motion. In this chapter, we'll have an overview of what a force is, what do forces do, how do we categorize forces, discuss Newton's first two laws of motion, and what is the third law, identify forces. In Chapter 6, we'll focus on forces, what do forces do, in terms of, in particular, Newton's first and second law. And we'll think about it in terms of forces are the cause for the effect being the change of motion, the cause for the effects we've been discussing in the previous chapters, the effects being the constant acceleration in our kinematic equations and our graphs and in other examples we've done of motion and change of motion. What is a force? Anything we can categorize as a push or pull that acts on an object and requires another object, which your textbook calls the agent. So something pushing on or pulling on something else. If an object is in contact with another object and it pushes or pulls on that object, then we can categorize it as a force. If it's not an interaction between two objects that push or pull, then it is not a force. You may be forced to do your homework, but that is not a force in physics. If an object is not in contact pushing or pulling on another object, it is not applying a force in the sense we mean of a force in physics. Such as, there is no force of you on the floor if you're not touching the floor. You may be sitting on the chair, and the chair is applying a force on the floor, so you're applying a force on the chair by you sitting on the chair, and the chair is applying a force on the floor. But if you're not directly in contact with the floor, you don't apply a force in the way we mean force in physics, because you're not in contact with the object. Only objects in contact with other objects can be forces. In our lower picture, we see the cue ball is in contact with the cue stick. Therefore, it's a force, a contact force. Forces depend on the direction. How much you push on something or pull on something is important, and where you push or pull on it. If you push on, pull on, if the stick hits the white ball at the top or the bottom or the center, it'll have different effects, from spinning it, from top spin to bottom spin, to directly changing its motion without making it spin. Push against the motion, it slows it down. Push with the motion, it speeds it up. Push out a direction to the motion, it deflects it. Where the force is applied, the direction of the force, the push or pull, is important. Therefore, a force is a vector. And we represent a force vector with the arrows as we've represented vectors up until now. It's another vector whose properties of vector addition and components fit what you've learned up until now. The bat making contact with the ball in the bottom picture is another contact force. We have two categories of forces: contact forces and long-range forces. Almost all the forces we'll discuss are contact forces, and the two long-range forces that we have are gravity and the electromagnetic force. Most often, the long-range force we'll have in our problems and be discussed will be the force of gravity. Oddly, gravity reaches out and pulls on objects, in a sense, just the same way as if it was a contact pull. The sun reaches out and pulls on the earth to whip it around, always the same way. The same as if there was a string attached from the sun to the earth to whip it around, with the tension in the string being the same as the force of gravity. Or as if the moon was attached by a pole to the earth, and that pole, that contact pull of the pole, whipping it about the same amount that the gravity of the earth whips around the moon. Oddly, gravity, electromagnetism, those long-range forces, these forces acting at very great distances, act the same way as contact push or pulls. So what do forces do? Well, from your illustration from your textbook here, if a force is against the motion, it slows something down, such as the snow or a rough surface pushing against the sled slows it down. The smoother the surface, the less the push, the less it slows it down, as we see in the middle picture. If the surface is so smooth that there's hardly any push against the motion, the object remains in uniform motion. It doesn't slow down. So in the absence of any forces acting on an object will continue moving forever in uniform motion. Motion needs no cause. Forces are about the change of motion. You force something to change its motion, to change its speed, or to change its direction. But you don't need a force to have motion. If the surface is sufficiently smooth, an object will remain in motion without forces. You saw this in the first ill. A ball rolls along a smooth surface. Without you pushing on it, it maintains its motion. If you do push on it, you can speed up or slow it down. Or if the rough surface pushes on the ball, it speeds it up or slows it down. So it slows it down for the rough surface, and it deflects it. So forces are about the change of motion of an object. Multiple push or pulls add together. The same way we add vectors by vector addition. A net vector, a net force, changes the motion. If there's no net vector, it doesn't change the motion, balanced or unbalanced. Forces vary with effect. You can push an object, you can make it flip over or spin one way or the other. We'll discuss this type of forces, the location of forces on an object, called torque, in a future chapter. The force vector is represented by an arrow, just like any other vector. The direction of the arrow is the direction of the push or pull. The length of the arrow is the amount of push or pull, the magnitude, strength, and numerical value of the force. Its units are newtons. The tail of the vector, the force vector, will always be on the object. This is our rule for this class. The force vector's tail is to be attached to the object. This will be useful when we have multiple forces and multiple objects. Our analysis is easy to follow when we follow these rules. Adding up vectors whose tails are all on the same object that relates to the forces on that object will be a clearer and easier task than having our forces distributed throughout an illustration where there's multiple objects, harder to figure out what's going on. Let's say this object is a crate, and somebody is pulling up and to the left on this crate, and somebody else is pulling up and to the right. So you have two forces, two force vectors related to this object. These two forces are trying to change the motion of this crate. The crate's originally at rest, and two people are pushing, both up, but one's pushing up and to the right, one's pushing up and to the left. Notice the tails of these forces are on the object. So, what is the net change in motion, i.e. the net force, on this crate, on this object? Mostly left, mostly right, mostly up. Left, right, then up. Submit your answer on Blackboard. We can analyze this question by doing vector addition. A force vector is like any other vector. It has the same properties. Vectors can be broken down to components. Vectors can be added head to tail, and their components can be added head to tail. There is vector addition, giving us a net force for the head to tail method. Here's breaking down a vector into its components. The force to the left is the same as the force to the right. The forces up add directly to be the same amount of the net force up from the head to tail method. Whether it's by components or direct addition of the vectors, we have the same result. The net vector is pointing up. So the net change in motion of this object is mostly up or entirely up. So what is a net force? It's not a special type of force or different from a force. A net force is a vector like any net vector. It's another vector. Therefore, it's just a force. A net force does the same thing that any other force does. A net force is a push or pull. It's the resultant push or pull, but the net force is the one that creates the acceleration. The net force changes the motion of an object. So a net force is represented by a vector whose tail is on the object, just like any other force. So whether looking at a force vector or a net vector, just depends on the label, but the result is a net force changes the motion of an object. If there is no net force, then the object does not change its motion. Notice I did not say if there's no net force that the object is not in motion. If there's no net force, the object does not change its motion. Force only relates to changes of motion. Net forces are only about a change of motion. An object can be in motion with no net force. It'll just stay in motion, like the sled in the previous example and the ball rolling smoothly, rolling on the smooth surface in uniform motion. Uniform motion is about no net force. Net force is non-uniform motion. We label the force vector to follow the rules of what a force is. It's got its direction represented by the vector and its amount. We label the force vector to represent that it's one object interacting with another object. Forces act on objects by other objects and thought of as push or pulls. So every force should be written in the form of F, the force, of object A on object B, or object 1 on object 2. Meaning that object A pushes on or pulls on. Whether it's a push or pull, we cannot distinguish. So FA on B means object A pushes or pulls on object B. In our lower illustration, the table is pushing on the book. It doesn't have to be animate objects. Pushing down on the table pushes back. The table, like all matter, is made up of atoms. Atoms are bonded together as if the atoms are balls on springs. So what happens when you compress a spring? A spring pushes back. These springs are the electrical attractions, the bonds are the chemical bonds. And so the book presses down on the table. It presses down on this tight bed of springs, this tight bed of atomic springs. The springs push back. Or in short, the table pushes up on the book. Force of table on book. In the middle illustration, it's force of hand on wall. She pushes on the wall pushes back on her hand. There's a force of the incline on the frog. The ramp or the bark is pushing on the frog at an angle. The lowercase n stands for normal. Normal is a mathematical way of saying the force or the vector or anything is pointing perpendicular to the surface. The normal direction is perpendicular to the plane to the surface. So normal force is any force in the direction of the normal, in the direction perpendicular to the surface. But it's still a force that follows the rule of A on B, just the direction. All these forces here would be normal forces. Force of table on book is in the normal direction. Force of wall on hand is in the normal direction. Force of ramp on frog is in the normal direction, where the normal direction is perpendicular to the surface. Newton's laws. A net or unbalanced force changes an object's speed or direction. If you have a push or pull that doesn't cancel out, you change the motion, non-uniform motion. A net force is the cause for non-uniform motion. This is a statement of Newton's second law. Sigma F, adding up the forces, if it doesn't cancel, we have a net force, an unbalanced push or pull, which results in the mass being accelerated. Or, if you push or pull on an object, This Newton's second law tells you how the object changes its motion. The first law is if there is no net push or pull, if you add up the forces and they cancel or there are no forces, then there will be no change in motion. It does not say there is no motion, it just says the object will not change its motion. Newton's first law is about uniform motion. Its velocity won't change, its velocity will be constant. It could be constant at rest or constant with some speed in some direction. It'll be in uniform motion. Or, if you don't do anything to change the motion, by pushing or pulling, it won't change its motion. Let's look at 5 force diagrams. Your author, the textbook, will call these free body diagrams. 5 force diagrams of just one object. If an object is gaining speed upward, this is a possible force diagram. We have a force up on an object and a force down. Well, adding these vectors up tells us there's a net force. There's more force up than down, so we have a net force up. And from the conditions of this situation, the velocity is up because we're told it's going up. I can't look at the force diagram and determine whether the object is going up, down, left, right, in, and out. We're told it's gaining speed upwards. The velocity is upward. The two forces I have are in balance. More force up than down. The net force is up. The velocity is up. Pushing in the direction of motion, net force parallel to v, means gaining speed. The direction of the net force by Newton's second law is the direction of acceleration. If the net force or the acceleration is up and the velocity is up, you know that acceleration parallel to velocity means gaining speed. So now, net force parallel to velocity means gaining speed. If something is moving upward at a steady speed, it's in uniform motion. So the net force is 0. We're not going to change the motion. It's at a steady speed. There is no acceleration, uniform motion. So our object, if it has a force up, must have an equal force down for the net force to be 0. Does not mean the object is at rest. The object will be going to the left, to the right, in, out. We're told it's moving up. We cannot see that in the force diagram. We just know whatever motion it has, in this case moving up, it's going to continue with that motion at a constant speed and a constant direction. It'll be in uniform motion. If an object is slowing on its way up, then there's a force up on the object, but there must be a greater force down. I add these two force vectors, and I have more force down than up. I have a net force down. By the addition of these vectors, I have a net force down opposite the motion. If I have a net push or pull opposite the motion, it's slowing. You pull against the motion or push against the motion, you slow something down. So net force or acceleration anti-parallel to the velocity means slowing. In this case, we're told the velocity is up. The net force down means the object is slowing. If an object is gaining speed downward, then this object has a force, let's say, up, but has to have more force down in order to gain speed, in order to be pushed on its way down to gain speed. So my net force is down. Again, we're told by the situation the velocity is down. Velocity is parallel to the net force, parallel to the acceleration, so therefore it's about a gain in speed in the direction of the velocity downward. Notice this force diagram is identical to the force diagram in the previous slide from number 3. Identical force diagram. In 3, the force diagram represented velocity up. In 4, this force diagram is representing a velocity down. In 3, the identical force diagram was about slowing. In this 4, this identical force diagram is about gaining speed. Point being, identical force diagrams, you cannot interpret motion. The previous force diagram for 3 was about slowing because the net force was opposite the motion. Here the net force in the identical force diagram is with the motion. We have to be the motion, the direction of velocity has to be stated. It cannot be interpreted from the force diagram. The force diagram does not tell you gaining speed or losing speed. The force diagram with velocity can tell you that. Something is slowing on the way down, meaning the velocity is pointing down. Then we have an object, let's say, with a force up and force down. But if it's going down and slowing, we must have more force upwards than down. So that we have a net force up, an imbalance up. We're told the object is going down, so net force anti-parallel, acceleration anti-parallel to the velocity, means it's losing speed. Or, push against the motion, it slows down. Notice this force diagram, number 5, was identical to the first diagram. Same force diagram in 5 and 1, but we're told the velocity is up in 1 and down in 5. Therefore, in 1, the identical force diagram with the velocity was about gaining speed. This identical force diagram as in 1 in this fifth example is opposite the velocity, so it's about losing speed. Again, looking at the force diagram, you can never interpret motion. Only the direction of acceleration, only the direction of the motion is going to change if there's an imbalance, if there's a net force. Here we have a dummy driving a car. It hits the wall. Before the dummy hits the wall, notice he's moving into the dashboard. But while he's moving into the dashboard, there are no forces on this dummy to slow him down or speed him up. He's not wearing a seatbelt being a dummy. There's no airbags or seatbelt to slow him down. So the dummy moves at the same speed he had while in the car before the car hit the wall. If the car, let's say, is going 50 miles an hour, then the dummy is moving at the dashboard at 50 miles an hour. He's keeping the same speed. The dummy is in uniform motion until he hits the dashboard. The dummy is exhibiting the Newton's first law, uniform motion, until hits the wheel, the dashboard, and the windshield. Until a force of windshield, force of steering wheel, force of dashboard on dummy, a second law example, slows the dummy down, forces against the motion of the dummy. The dummy is in uniform motion of Newton's first law while moving at the speed of the car towards the dashboard and windshield without a seatbelt to slow him down. Then the sudden great force from the windshield and dashboard suddenly applies Newton's second law against his motion to slow him down. This person is in a car accident. Looking at the image over time, the person, 3 images of this person. Time flows to the right. The person in the images was in a car accident. Was this person hit from behind or from in front? Submit your answer on the blackboard. Here we have a cart. The vector to the right of the cart is a force vector. The cart is being pulled by that force vector in the direction of the force vector in the positive x direction to the right. A cart is pulled to the right with a constant, steady force. How will this constant, steady force affect its acceleration? Will the acceleration graph look like A, B, or the graph in C? Submit your answer on blackboard.